Hi guys, section 2 today for chapter 14. We're talking about just ways that we can measure matter, okay? Little science joke coming. You have mass, you have volume, you matter. Oh, jokes. Okay, so how do we measure matter? First of all, we can take the mass, and that's how much matter there is, crammed into a substance. And remember, we've talked about mass and weight before. Weight is dependent upon gravity. Mass is the same no matter where you are in the universe. Okay, the mass is literally how much matter there is into the object. I've got two objects here, same size. One is clearly heavier than the other. Okay, since they're the same size, what that means is that the heavier one has more material crammed together. Okay, which is going to lead us into talking about density, and you can kind of see that picture right there that shows how there's more substances in this one, more particles of matter. So we would say that this one is more massive. Now, a lot of times we use the word massive to talk about size, but scientifically speaking, it's really referring to the mass of the object. This one is a lot lighter. There's less material in it, so its mass is less. Okay. We can also measure the volume. That's how much space objects take up. These both have the same volume. They're both about an inch cube on each side. Looking back at mass, we'd use common units like grams and kilograms, but we could also use the American system, pounds, ounces, things like that. Volume is commonly milliliters or cubic centimeters, okay? If you've ever watched a medical show and they talk about cc's, they're talking about an injection, like how much medicine to give. That's cubic centimeters. That's what the cc's are. And then we put both of those measurements together to talk about density, okay? So if we divide the mass by the volume, that gives us the density. That's a Greek letter that symbolizes density. Don't worry about that so much. And then we would label our density with both that mass measurement and that volume measurement. So it could be grams per milliliter, grams per cubic centimeter, kilograms per liter, something like that. So you would have a mass unit over a volume unit, okay? Now just a little review on density. Remember that it's a comparative thing. Typically we talk about water, right? Water has a density of 1 gram per milliliter. If something is put into the water that is, here we go, so I have a little tub of water here. If something is put into the water that is less dense than the water itself, it's going to float. You see that? Floating right up on top there, okay? If something is put into the water that is more dense than the water, it sinks right down to the bottom, okay? So a lot of times we just talk about density in terms of comparing them, all right? And then density can also be used as one of those characteristic properties, but just within the same state of matter. For instance, water always has the density of 1 gram per milliliter, but that's liquid water. When you freeze water, it actually becomes slightly less dense. That's why ice floats, okay? But within the same state, density can be used as a characteristic property. Okay, a couple of different ways to measure density. Volume, if it's a nice straight-sided object, the volume can be easily measured. Length times width times height, and that's how you come up with the volume. But most objects aren't regular like that. So if we got this little dinosaur guy up here, he clearly doesn't have an obvious length, width, and height that we can measure. So we would measure the volume by something known as displacement. We would measure how much water we have. Okay, we would look at that starting point right there. Then we would put our object into it, and that object is going to take up space. It's actually going to move some of the water out of the way, and so then this difference, this water, represents the volume of that object, okay? Now this is kind of going back to that idea that density is a characteristic property. Let's say I've got this dinosaur, okay? Let's say he weighs 10 grams, and he displaces actually 20 milliliters of water. So I would divide the 10 by the 20, because it's always mass over volume, and that would give me a density of 0.5 grams per milliliter, okay? Well, if I cut that dinosaur in half exactly, like not top and bottom, but like right through the middle, okay? Then he would have a mass of 5 grams. Then he's only going to displace 10 milliliters of water. So again, 5 divided by 10 is going to give us the same density, okay? And so that's how density can be used as a characteristic property. It doesn't matter how much of the object you have. When you cut a piece of it away, it's going to weigh less, it's going to have less mass, but it's also going to have less volume. And so that's a proportional difference, and that's why the density would stay the same, okay? Last thing, we've got this law of conservation of mass. Now, if you remember back, we talked about the law of conservation of energy, and that stated that energy cannot be created or destroyed. Well, this law really just replaces the word energy with mass. Mass cannot be created or destroyed. It can only be changed, just like energy, okay? And the example that's always used is this example of burning a fire. And it's suggested that if you take the weight of the logs, but you can capture the smoke particles and the ash afterwards and everything, that the mass of both the beginning and the end would be totally equal. That's not really true, okay? It's much more complicated than that. At this level, we're usually taught that the law of conservation of mass and the law of conservation of energy are totally separate things, but they really work together, okay? And that is because of Einstein's famous equation right here. He actually was able to relate energy and mass together. And so for this example up here, you're producing all kinds of energy with that fire. So if you take the energy into account and the mass before and after, then everything is equal. And that's still a very basic, description of it. But if you take both the law of conservation of mass and the conservation of energy into account at the same time, then your starting and your finishing amounts are always the same, okay? I believe that is all for today. It is.